I don't always talk about shaders, but when I do, it's at Fablo.
Okay, go.
Right. Hi, everyone. Before we actually go into shaders, I would like to take a step backwards and say some words about myself. My name is Alex. I'm a software developer since 2006. I worked for various companies, and last year I decided to just resign and do game development full time. Not in a paid company, not for somebody else, but actually work on my personal projects. Unprofessionally, my affair with game development starts way early in '98. Obviously, there was not much in terms of hardware. Today, we're actually really ahead. We're even ray tracing in real time. So there's a lot of potential out there that needs to be, explored. Hello. Don't worry. Okay. So I started with Borland Pascal. I had some assembler game development examples, and I started with MS-DOS, the old traditional way of doing game development, and progress with years. I've noticed at some point there is something called DirectX, and it was DirectX 5. I've grabbed my hand.
I voted for that. I was there with him.
Yeah, it was nothing really but some APIs of the DirectX. Obviously, I was interested in Direct 3D, and you would play with those, create textures, you would have to create essentially your own rendering pipeline, but it was fun. However, a few years later, fast forward, we get DirectX 8, which I think, if I remember correctly, it was the first DirectX to feature shaders. They call that fragments. And the language for those shaders is high-level shader language, HLSL. You will see that throughout, not only in Unity, but you'll see that regardless in where you actually develop your game in. It's, if I could say, it's game engine agnostic. It's a CG language. It's somewhat universal. But engines kind of wrap up the actual CG code to make use of it in their own specific way, and we'll see how Unity does that. And what was interesting with the shaders in DirectX 7 is it was the fact that I could do stuff that was otherwise impossible or really unperformant to do with traditional, take the image, do this and do that. For instance, I've created the depth of field effect. Coming with a background in photography, I was really amazed that nobody actually thought about putting depth of field, the blur behind the objects in computer graphics, which would add tremendous realism to a scene. And I've done that in 2004, and it was not something that the industry was actually really aware of. You would see depth of field in Crysis in 2007, and since then it's quite a common effect to see. But it allowed me to create that effect in 2004 using shaders. So I kind of kept them in the background as being something potentially, really value-adding asset I could have. And at some point I stopped game development for good, and a few years ago I stumbled upon Unity, and I saw that, hey, you know what, I can do this in Unity as well, and it's actually so much easier to work with the shaders in Unity. Unity has a lot of housekeeping tooling for you to develop and interact with Unity. We've deviated a bit from I'm Alex. This is I explain a bit of why I'm a person that essentially tells you about shaders. I presented a bit my background. So I have a non-professional game development background, but I also come from a photography background. As you can see, I like colors very much, and besides color, I like post-processing. None of these photos are real. They're not straight out of the camera, just like that. Some of these even have the skies completely faked. Can you guess?
First one's on the left.
First one, yeah, sky is completely removed. This one, however, here the sky is the real one, enhanced a bit, but it's the real one. So I always looked at game development as something that doesn't stop with, putting the geometry, putting the materials, dropping the lights, and that's it. I think post-processing adds a lot to the final image that we render. And we'll see how shaders can be used to actually gain more value from our rendering. I also like guns. I said that before, but it didn't change since the last presentation, so you'll always see it here. And I started some brands, if I could name them, a few years ago. Fragment Games and Destiny Squirrel are. I'm planning on releasing games under those names. Fragment Games is mostly targeting PCs, consoles, and big heavy games, and Destiny Squirrel is rather targeting mobile games. And Omnistar Technologies. What is this? Well, in games that I will release under these two brands, there's a lot of technology behind, and the technology is created under that name, because I also use this to sell technology on the asset store. So, shaders. Finally, we got shaders.
One moment.
Yeah.
If you can read the questions there.
Oh boy.
There's something about depth of field. I think
The depth of field is normally something for the eyes to focus on one thing only in a game. You cannot really tell a game what you're looking at without moving around. The eyes just move around. I didn't really get the last one, but yes, I think the point is you don't just drop depth of field and you stick with it. Obviously, that's for some isolated scenes. In fact, if you look outside and it's a really deep scene, a really huge scene, it's unlikely that you will see any depth of field because of the optics physics. But sometimes when in certain situations, you could have depth of field really enhance the image. For instance, when character grabs something, looks at that something, maybe you can drop depth of field, you blur the entire background in a photorealistic way, so that the focus is on the object that you're looking at.
It's like you dictate which is the focus point.
Yes, this is the main idea that in cinematography, it's used to redirect focus towards some object. And sometimes even in movies, you don't see like big blur everywhere. It's rarely used, and it's used only when it makes sense. So in game development, this should be the same case. Back to shaders. If we really need the shaders, we could probably live without shaders. Without doing extra shaders, because everything that you see in a great game engine has, visually wise, has some bit of CG code at its core, and we'll see what that means. This is a question I've asked, in the past presentations, and I'm coming back to it because we'll see how that relates to shaders. So what makes good graphics? From my perspective, good materials, good lighting, post-processing in VFX. How does that relate to shaders? Well, each of these actually rely in one way or another on some shader code. For instance, surface shaders, use materials that you drop on the surface, on the objects, use shaders to render the surface of that particular material, of that particular object. Even lights can be done entirely using shaders, because Unity has some buffers, and one of those buffers is the lighting buffer, and you can actually hook into the rendering pipeline and say, you know what, give me the lighting buffer, you write something there, which essentially means you light up the lighting buffer, and then Unity takes what you've altered there and produces actual lights, and that's actual light data. Post-processing. Obviously, post-processing is the most obvious thing that makes direct use of shaders. Every post-processing effect has at least one shader at its core. We'll be focusing pretty much on the post-processing shaders, and I'll explain you why we will not do so much surface shaders in a moment. Obviously, VFX uses shaders, but not like, okay, if I do a fire, I need a shader necessarily. Rather, the particles that you render with VFX are basically materials applied on some planar geometry that the particle system generates, and those particles look the way they look because they have assigned a material, and that material has a shader at its core. And more. We'll see what and more means afterwards. Surface shaders. Anyone mind to explain what is a surface shader? First of all, who uses shaders like in actual, hey, I've modified a shader, or I've created a shader, or I downloaded a shader?
But I use it with the node space, with the amplifier. I'm not handling
No, I mean
I'm just
code-wise.
Not code, but it's the same thing. Basically, I need to do the same math behind and how to understand.
Okay.
What nodes go, what inputs go.
Okay, but it's still visual scripting of shaders.
Yeah. It's not code.
And that is the particular reason for which we're not going to go very deep into surface shaders, because you have a lot of tooling, a lot of support that can help you achieve a lot of looks with surfaces. However, you don't have much options when it comes to image effects. As far as I'm concerned, I don't know. I haven't seen a visual scripting tool for
Amplify.
Yeah, but for
also for process. Yeah.
Can you do ray tracing, raymarching, volumetric rendering?
I don't know.
I'm pretty sure you can do post-processing, some basic post-processing you can do, maybe even more advanced.
The image stream and whatever you like with it, just like in Unreal. So it's
Okay.
basically the same. Even the nodes, their functions.
So instead of sticking the material onto objects, it's a screen space quad. Okay, yeah. I guess everything you can do basically in I'm not sure what's the extent in terms of what you can do with that.
I don't think there is any. Maybe they haven't implemented everything that's available in GL, but
okay.
basically everything. You can even not the lighting, the light shader, but you can pretty much fake the lighting with the shaders. So I guess that are light shaders.
I'm wondering if you can, hook into the rendering pipeline with amplify shaders. So like if you want to alter the G buffers, maybe G buffer 0.
I know what you say. I don't think you can go that deep. No, right?
So
I know what you're saying, but
they can't fake command buffers, like.
I'm not sure. Really, I don't use it that deep. I use it to make something custom if I need it, or to modify I mean, because I cannot touch the already written code, I have to make it from scratch.
Yeah.
But it allows me to come up with, maybe I want something that it would take too long to find the resource to code it. Like, for example, a water shader, yeah? It's the ocean shader. You have to simulate the mathematics behind the waves, and it's much cheaper it's much easier to use it, because you can experiment easier.
So you see the effect in incremental steps quite easy.
Yeah.
Well, yeah. That's one thing. But, it's if you, and I'm glad you brought the ocean because it's exactly what I'm doing at the moment in my particular work. I've noticed one thing. When you modify a C# script, depending on the size of your project, it may take very little time or a little more time. But if you're actually modifying shaders, you generally don't have so much shader code in your project, and it compiles just like that. And I got into the situation where I was doing more things in the shader so that I don't have to, update the corresponding C# script. And yeah, it's blazing fast, but you're actually, when you say it's fast from a productiveness point of view. Yeah. Okay. I saw this movie at some point in time. You know what the movie is, right? And I've seen these, and I like those. And when I started working with Unity 2 years ago, I said, you know what? I need to get my hands dirty and learn something. And let's start with this. Let me start with something I like. And the result was quite pleasant for me. What is that? That's a shader on quads. So essentially have a back of quads, and each of that quad has a shader. The shader grabs the background and warps the pixels based on some normal map I input. And also I have another map, another texture that, depending on its illumination value, amplifies what's behind what's in the grab pass buffer. And I was amazed how easy I could, reproduce that effect. And that kind of made me go deep further into actually writing more complex shaders. I will go through this presentation and then we'll go to the practical sides of things. I think we'll finish really fast the presentation. I don't have too many slides because I want it to be, a real tutorial-like presentation. So bear with me. There are not so many slides coming. However, so we've seen we have surface shaders. Of course, when you create a new material, there's an implicit shader that is being assigned to that material. Do you know what that is? The standard shader, right?
Okay.
And the standard shader allows you to, drag some sliders, drop in some textures, some maps, basically, to achieve per pixel look. Usually you would put those on objects, but sometimes your object is the actual screen, And I guess the whole point with the image effect shaders is that you have an image, the final image that's being rendered, and you want to enhance that, and you want to enhance, every pixel on that particular shape. I see. Yeah. Thank you for making a mess here. Okay. In contrast, the image effects shaders address every pixel on the screen, and they do something with that. And more than often, they don't really rely just on what's on the screen graphically. They also use motion vectors that are being generated in some camera buffer. They use the depth buffer to make sense of the geometry in the scene. And they use a lot of other things. But the point is, you put that on the camera, you snap the component on the camera, and magically, whoa, you have screen space reflection, or you have depth of field, as I said, or you have ambient occlusion. We will focus more on these because I want to present you some techniques in achieving some great effects with that. Let's see what else we have in presentation. We'll skip it really fast. Yeah, Unity model behavior flowchart. So obviously you don't see that, and it's not meant to be seen. If you will be interested in it, you can download the presentation and take a deeper peek at that. What's interesting for us is this section here. So right after initialization, which is awake, of course, you have physics, you have input events, you have the game logic with update and and then you have the scene rendering. And that's very interesting because here you have a lot of callbacks that you can override in your mono behavior script and essentially hook into this flowchart. How many of you know the onRender image? No. All right. And I assume none of these sound familiar, or you never worked with those. Okay, great, because I have something to teach you. So, it makes sense. Right, and this is the rendering pipeline of Unity. There are two rendering pipelines. We have the forward rendering pipeline, which starts with rendering the depth normals, renders the opaque geometry, and then follows this path where renders the opaque image effects, renders the skybox. It's really weird to me. Yeah, exactly. It's like, why in the world are you rendering the skybox after opaque geometry, after image effects? It's silly, but this is how it does. Then it renders transparencies and image effects. You see, there's two points where you can actually render your image effect.
Can you shortcut the path over there, or are you always forced?
No, you're always, in fact, you're not controlling this. This is embedded into Unity's. Yeah, it's the actual rendering pipelines. You can select the rendering pipeline on the camera. You can use forward rendering. If you have a low tier end device like mobiles, you would not use deferred shading. But if you have a high end, hardware, you can use the deferred shading. And in the deferred shading, first it starts with rendering the G buffer, and that means rendering every geometry on 4-5 separate textures. You have the depth texture, you have the diffuse texture, you have the, what else you have? Smoothness and smoothness and specular color. You have the emission buffer, and there was another one, and the depth. Yeah, and at that point, it's like Unity is, on this board I draw the diffuse color. On this board I draw the normals. On this board I draw the smoothness. On that board I draw the depth. And then there's something that combines all this and gets you the final render that you see. And we can actually peek at those if we go into the scene, and click on this small drop down here, and by default it's shaded. It means you see the final composite result, or you can look at the albedo and look, that's the albedo color. You can look at specular, but since nothing is specular here, let me just quickly add some specular on this. That's the only specular object in the scene at this point. Of course, we have smoothness and if I drag the slider, you see just the smoothness buffer, what's in the smoothness buffer, and the normals, which, depending on how the object is, you'll have more or less normals. For instance, if I drag these normals here, you can actually see the super extruded normals on this object. Let me put this back to 1. Yeah, and combining all these, Unity creates the final shaded image. Why am I telling you this? I'm telling you this because you're actually able to hook into almost every point in the rendering process. The easy way is with onRender image, which allows you to hook here or here. The not so easy way is using command buffers. It's like, when you use command buffers, it's like saying to Unity, hey, you know what? I know you're rendering and you have a lot of steps in your pipeline, and there's no callback for me to hook into a specific point. Maybe I want to hook right after the G buffer is being created because I want to create some virtual object in the scene without actually using geometry. I have a super smart shader that does a complex object and puts it in the scene. I need to do this right after you create the G buffers, render them, so that my object is being accounted when the lighting packs comes. And this is where you create command buffers. You create a command buffer, you say, this is the event I want to hook after, and you instruct the command buffers with some drawing calls. And what you draw there happens at this point. But those are a bit complicated. We'll not be doing that today. We'll be mostly doing hooking into these two points because it's a lot easier. World space image effect shaders. Does it make sense? Does it make sense? How the hell is it world space if it's an image effect? Like, how do you make sense of the space?
Maybe we need the buffer to
Yeah. Can you give me an example of a world space image effect?
maybe something like a scanner, like a No Man's Sky scanner.
Yeah.
Goes into the
But how about an object?
an object that uses.
No, the rendering of an object. I mean, if we think about movie industry, right? What do? They actually take an actual shot, they track the camera, and then using that camera they render objects in the scene.
Yeah.
Well, you could have a shader that does that, can you? Without actually having the object in the scene. As you said, like an ocean. You don't have to physically put the ocean in the scene. And, you drop an effect on the camera and bam, the ocean is there. See? We'll see how we can do those. Like this. This ocean is entirely rendered using one shader. Just one. And of course, because it's the shader that does the rendering, essentially every effect that the ocean has on it. You have some specular lighting here. You have some surface, subsurface scattering. You have some diffuse reflection from the sky and many other things happening here. It's in your complete responsibility. So yes, it takes a bit to write one of these shaders, but then it's screen space. It has some inherent benefits. Well, for once, you don't draw too many vertices. You just have one big quad on the screen. Because remember, this is literally as going into Photoshop with your rendering and pasting an ocean over it, but accounting for the camera position, rotation, and everything else, right? So that when you actually go in the scene and you move the camera around, the ocean slides, it doesn't stick to the screen. So yeah, this can be achieved with screen space shaders. Command buffers. As we said, onRender image is a little too late. If you're here, but you want your shader to actually be accounted in the lighting pass, you need to hook so much earlier. Otherwise, you'll be late at the party. We don't want that. So you can hook in various places in a more refined way using command buffers. But command buffers are a little bit trickier to use. So thank you. Done. Home. Right. Basically, we've ended with the presentation from a slide, from a PowerPoint wise. Now we get to do the nice, the interesting bits.
Do the ocean?
Yeah, maybe we do the ocean. I don't know. First, let's see if we can control, this flow of image effects. How do we actually create and set up an image effect? I mean, if you're the developer of the image effect. Well, everything starts with a shader. So the basic idea is you create a shader, you create a material, you draw a quad, but with that material, so that when the renderer draws the quad, it asks, hey, for this pixel here, I need to generate a color. I need to output a color. What's the color? And your shader says essentially tells him the color, and we'll see how we tell the renderer for each pixel on the screen what color to draw. Let's create a simple simple shader. Create shader, and we have some options here. We have a standard surface shader. Since we've mentioned surface shaders, let's create one, and I will call it red object. And Unity already gives you a lot of infrastructure, a lot of, if you wish, high-level framework to work with. So you're not completely, create your shader. I don't give a shit what you write in there. It creates you a shader that is based on the standard shader. Right? So we're kind of cheating here. It's not exactly from scratch, but for the sake of this example, we're going to go with this. The point is, we can write into the albedo, into the metallic, smoothness, and alpha. And when we can do that because this shader, let's see, we'll create a material based on this shader. I'll create a new folder, call it surface. Create a material, right? And red object. It's not red yet, but. So how can we get our shader? Well, we have to look at its name, basically. And by default, it puts the shader under custom. But screw it. We're here to learn about shaders 101. So now, you see how fast it compiled the shader? You didn't even see it. And now if we go to shaders 101, guess what? We have the red object. And we assign the material maybe on this cube. And the most boring cube in the world. It does nothing, right? It's just a boring cube. But it's affected by light, yeah? It's affected by, it takes into consideration the color, the main text, the glossiness, the metallicity that you input into this particular material. But let's add another parameter to it. And I'm going to add a parameter here and say, float, what do we call it? Redness, if that's a thing. We have to, if we want this particular parameter to show up as a property in the shader, we have to put it here in the properties, obviously. Although, if you create the shader using code and material using code based on that shader, and you set the material properties from the code, you don't have to put here anything. This is just for the material to display them. That's it. If you're controlling the shader via script, you don't need this section. But we're not doing this now, so I'm going to put it right here. Because my cool redness, you can put it a range, range from 0 to 1, and we have to give it a default value of 0.0. Sometimes you have to check if your shader compiles correctly. If it doesn't compile correctly, it will show up here. It will give you an error. We're going to go through what all these means later a bit. Now let's just focus on this parameter, redness. And what do we do with the redness? Well, I know this has a field called emission. And I'm going to create a red color and multiply it by the redness factor. Too much data. Okay, because it's float 3, not float, okay, float 4. No, it's float 4. And my cool redness showed up. Let me bring down the color so, we can see that. Metallic, no, we don't want that metallic. When we increase the cool redness, it's just cool redness, right? Now we can pat ourselves on the back, first shader. But, this isn't very interesting for me. So I'd rather go to the next level and create some image effect. Obviously, you can tamper with these parameters here and write virtually every field here with whatever you wish. But we're not going to dwell into that too much. Let's close this and let's create a screen space shader so that we process a little bit the image. But first I want to get rid of this shader and, kind of get a normal queue here. So, as I said, how do we start? We start by creating a shader. In screen space, we're going to create a shader, and we're back here. Basically, these two are somewhat the same. They're used to create surface shaders, but this one is a little less supportive. So you're really in the void. You have to know what to write. It's like, hey, do whatever you want. So you can do whatever you want. So literally, you have to create your own rendering here if you choose unlit. That's why I said if you're creating a shader that's based on the standard surface shader, you get some advantage because it does the shading for you, and you can get to change the output of the shader after everything was done. That, of course, what's the use case here? So maybe you want the standard shader, but maybe the standard shader doesn't have something you would like to have. I don't know what that could be. You can extend the standard shader by creating a standard surface shader, just how I did it, right? I've created basically a red emission standard, although the standard has emission, but it was not exposed. Image shader is what we're going to do now. There's also a compute shader. Do you have any idea what that is? Well, apparently with a compute shader, you can instruct the graphics card to run multiple threads. You can define, a 3D set of threads, and you can assign work to them.
Basically like OpenCL?
It's exactly OpenCL. It's actually an interface to CUDA, and the language is CUDA. You have a main kernel, and that kernel is assigned to all your grid threads, which usually is 3D, and they do stuff in parallel. But that's not in the scope of our presentation today. So we're going to go with the image effect shader. What to call this? A very meaningful name. So what do you want to create with this shader? I want to create a post-processing, no, a color grading shader. I know there are tons of color grading shaders, but I want to show you how you set up a shader, no matter what you do in it. You know, I mean the tooling and the sequencing of actually using shaders is more important in this presentation than the actual shader code itself. Is if you're a complete beginner, where do you start? You know, and you start by creating a shader first, an image fix shader, and then you would have to create a material. The material could be created from C# code, but you could also create it as an asset. Not very nice, but to save time, we'll do this for the presentation. I'm going to edit this shader so that I put it into our own section of shaders. Hidden, because right now it's hidden, you can't even access it. Right? So we're going to put it in shaders 101, color grading shader. So now if we create a material with that, okay, create a material, and we're going to say color SS screen space. In fact, you know what? It's color grading matte. It's screen space, so it doesn't. So by default, it's standard. You know, it has the standard shader assigned. So what do? Well, we go and change the shader, obviously. Color grading shader. And it has a texture. We don't even need that texture. You can set the render queue from here. We're going to see we don't need to do this, as we will specify in the shader an actual render queue. So how do we set that up? For now, let me remove that parameter, because here we're going to work with the code. So basically this section here is not needed, but you have to have the properties section. Apparently it doesn't work if you don't have it. Yeah, I'm just curious. I need to do this. Oh, still works. Great. So you don't need this property section here. Now, what does this mean? We don't care now. What we do care, however, is the fragment code. This is the piece that you will engineer most of your time. And we have to draw a little bit of something before we go on, so so that you make sense of what I'm going to explain. So let's start with Paint, MS Paint. Let's try to envision what it happens when actually something is being rendered. So you have an object, right? Let me take that. Maybe a little bit thicker. Perfect. So we have a cube, the best cube in the world. So what's the point? It's being rendered on the screen. Thank you, I needed that.
Special effects.
We have SFX and VFX as well. So let's assume the renderer starts to render, yeah? And it takes every pixel on the viewport and it tries to ask what's the color at that particular pixel. In this case, it starts with that pixel there. Right? And why is that pixel there blue tinted? Well, because that pixel is part of a surface, in particular this surface, the surface of this cube, and the cube is being rendered using this particular material, right? And this particular material is based on the standard shader, and it has an albedo map, a normal map, and an emission, as you can see. And that pixel is rendered by the standard shader. Basically, the render asks you, hey, give me the color of the pixel at this particular texture coordinate. And if we take a look at that unlit shader, we get the input here. This is a structure we may define. We may alter this structure and add even more data but you have at least the vertex and the UV. You guys know about UV, right? Yeah? No? Does somebody doesn't know about you? Okay, so you have an object, right? Like this square here. And you have a texture that kind of wraps on the object. But who dictates what's the position in the texture that is being rendered at the corner? It's the UV. Every vertex in the world has a UV. So this point here that makes up the rectangle, in fact that makes up the whole cube, is defined in 3D space, so in world space by 3 coordinates, right? X, Y, Z. But also has another 2 coordinates, and those are texture coordinates, or UVs. It's like saying, you know, wherever this vertex is in the world, I don't care where it's in the world, when you render something, take from the texture at that coordinate. And that's why the UV is a 2D coordinate, because it's in texture space. Right? Makes sense. So if I alter the UVs here, for instance, the offset, you see how it tiles differently, right? Or if I increase the tiling, sample more often. Okay, now that we know what UV is, you get that information here in the shader. And the shader has 2 parts. It has a vertex shader part and it has a pixel shader part. Why? Well, for once, it gives you the opportunity to actually change the vertices if you wish, before pushing them towards the fragment shaders, which is this function here. And you get this app data, which, as we said, we get the vertex and we get the UV. And this function is being called for every vertex in the world, right? So for that cube, for instance, we have a cube and we have a plane, we'll have like 8 plus 4, 12 calls of this function. And here you can basically convert the vertex from world space. In fact, it's from object space. Let's clear a bit the spaces. Because do you know what the space is? World space, view space, clip space, camera space. You see, yes, no? Well, when you have an object, every vertex of the object has its position relative to the object itself, right? So, for instance, if we take this cube, he's at the position 3, 0, and 0, 3, it doesn't matter. But everywhere we move it, regardless of where we move it, these vertices, they stick together. And that's because it's relative to the center of the cube. Most likely it's something like -1, -1, -1, +1, plus, blah, blah. So, but how do we move them in the world? Well, if we want to get the world space position of this vertex, we have to change the reference point. So we no longer reference based on the center of the object. So we no longer referencing, we're not placing ourselves in reference to the object, we place ourselves in the reference to the world. So then for every vertex here, we have to add this to get the actual world space position of its vertices, right? But it doesn't stop here, because you also have a camera. And when you move the camera, it seems that the object and the entire scene moves. It doesn't stick to the camera. So how do we do that? We have to, transform these vertices and basically tell them, hey, you know what? The camera is here, so subtract this, rotate that. So that's actually called the view transform. So the first transform that gets your vertex from object space to world space is the M transform. Yeah? The second transform that gets your vertex from world space to to camera space or to view space is the view transform. And there's another transform which actually transforms these pixels on the screen. That's the perspective transform. And you'll see the MVP transform, which is a multiplication of all these three transforms, which, if applied on a vertex, gets your vertex from local space directly in the clip space, so projected on the screen. Well, this is what this function does. Yeah, it actually multiplies with that particular matrix, with the MVP matrix, gets the world from object space, gets the object from object space to world space, from world space to camera space or view space, and from view space to clip space. Yeah, and then you get to transform the UV. Honestly, I don't really care about this. You can just assign the UV directly, just like that. That stuff here is taking care of some corner cases, but just for you to understand, at this stage, I'm doing nothing but just pass on the UV, because I'm going to need those here. And how many times is this fragment called, and when? As we said, when the renderer renders the object, it looks as it's at its vertices, right? And for every vertex, you get to transform that vertex. And ideally, you would transform the vertex from its local space onto the projected viewport, so that you get these positions right here. If you measure them, that's the result. But the renderer doesn't render just the corners, right? It renders everything in between. So how does it generate that information? So what is the UV here at this particular point when I'm pointing with the mouse? Or what's the space position or the viewport position? Well, it looks like our graphics card have up to 8 interpolators. So after this function is being called by Unity, for every pixel on the screen between its triangles, so if you have a triangle, right, let me draw a bit. So you have a triangle somewhere on the screen. This is 1 point, 1 point, and 1 point. At some point, the renderer renders the pixel, blah, 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 and it gets here, right? And in order to render this, he basically asks you, what's the color at this particular position? But he gives you the vertex position and the UVs at that particular position. And how does it do it? Because we're in a linear space, it does a simple interpolation. It interpolates the UV from here with the UV from here based on the position between, what an interpolation is? You do. You guys know what
Mathematics.
Okay. Let's assume we have Okay, we're gonna draw a little bit more now. 24. Okay. Let's assume we have two colors, right? We have red and we have blue. And we need to obtain a color in between, like halfway in between. What do you do with these colors? Let's say we have color A and color B. How do you get a one-to-one mix between these? What? Media, which is the average, right? How do you compute the average?
You add the two and split by two.
You add them and split by the number of them, right? Very complex math. But, you know, what if I want to have a control that kind of sweeps between these two colors? How do you get that in between, but not in perfectly in the middle?
So I have to you mean like in shader? I have to have the input for the color A, color B, and then
Produce a C that is a combine of the two colors, but based on one factor, based on, you know, a mixing ratio. Maybe I want 10% from A and 90% from B, or 60% from A, and well, you can use a linear interpolation for that.
That means if you are on the left side, you will have completed A.
Yeah.
On the right side,
So F, A, B, and we'll call this D, which is the interpolator value, will have to be A if D is 0. Yeah. A if 0, it will have to be B if T is 1, and it will have to be something if T is in between. Where there's a function called lerp from linear interpolation, and it's exactly with this signature. And basically, the shader language supports every data type possible you could throw into that. You can lerp vertices, you can lerp UVs, you can lerp colors, you can lerp floats, ints, whatever. And the formula for this is very simple, actually. You get A plus, you compute the difference between B and A, and multiply by T. Yeah. Or it's A multiplied by 1 minus T plus B multiplied by T. It's really like you would take 50%, 10% from the left, because this is what this means, and the rest of the percent from the right. And when you mix them, you get 100%, which is an in-between mix of those. But it's actually much faster from a execution perspective, a point of view, if you get A, B minus A, multiplied by T. And I saw somewhere in NVIDIA documentation, they computed with the other formula, which would be really a shame, because this one is much faster. It's exactly the same mathematically. This has just one multiplication. This has one multiplication. The other one has two multiplications and two. It's more expensive, but you know what? Remember this is lerp, yeah? And the cool thing about it is that it doesn't really stop at its edges. That's cool, right? Because you can call lerp A, B, and 2. Would you imagine what the result would look like?
straight red or straight blue. So just blue values.
No, we're in high dynamic range. We can exceed 1.
Okay.
Well, you have the formula, like, yeah, it's definitely
98% of A and 2% of B, right?
it's 2B, right? But remember, that's B minus A. Well, I guess the best thing, best you could think of when it comes to linear interpolation. You have one point, this is A, the other point, this is B, and T basically gets you something in between. Yeah? If you specify T at 1, you get B. If it's 0, you get A. But if you go beyond those, yeah, if you view it like this, it makes more sense. And this makes sense also in space. This is a 2D space, and this is the linear interpolation between 2 points, yeah, in 2D space. Y. So you can say, this is T, give me that point. If you apply that formula for every coordinate individually, you get the exact interpolation position.
You are relating here 2 between 0 and 10 so that you can understand something, but 2 can be 0.1, that is in between 0 and 1, right?
No, T can be whatever. Usually, if T is in between the actual values that you're asking it to be, it's called interpolation. But outside, it's called extrapolation. Because I can find out when this line extends if I give it the T that exceeds 0, 1 interval. And of course, this actually works in 3D space, where you have x, y, z, and you apply this formula for x, y, z, and it gets you the interpolated value. Now, if we come back to our example, this point here, the UV and the x, y, z vertex position is easily computed based on the other points. Yeah? And then it calls, for every pixel, it calls this function. And that's the fragment shader. That's the fragment part of the shader. And why is it called fragment? Because we have a triangle. The renderer splits this triangle into small pixels. Because at the end, it has to produce pixels, right? So these pixels are called fragments. They're fragments of the actual geometry. For every pixel, we have frag of a certain input, which input equals UV and vertex position. So he gives you this information. He interpolates the information that you define here. And this is filled in by Unity. If you write this, Unity will fill in the vertex value and will fill in the UV value. And basically what we're doing in the vertex shader is telling, okay, now in the output structure, which is the thing that will be passed to this function, because you can say, right, v to f, I, and the output of this is the input of the next one. But this one is not called once per vertex, as the third function is. It's called for every pixel. That's the frag. That's the fragment. And why do we care about that? We care because when we design and write screen space effects, basically our shader will handle every pixel on the screen, right? Because we're essentially drawing a quad, which is just two triangles on top of each other. And here we have UV 0 and 0, UV 1 and 0, 1, 1, and 0, 1. We will get for every pixel the interpolated UV for the pixels. So that's how we can locate our input, and that's how we can get to read from the input texture. Let's see that in action. So I will drop this shader and get to our, image effect shader. As usual, we have the vertex shader, and you can see there's nothing but passes on, and the interpolator of which is a hardware interpolator, calls the fragment function, and it gives you here an interpolated version of what you output there. Right? So you get the vertex position, which will not be interesting for us because we're in screen space. We don't really care about that. but we also get the UV, just passed on with no change.
So the output of the first function
Yeah.
is the input for the second, no other processing in between. Right?
No, except it's interpolated, because
The verb function is called, here the verb function is called 3 times. For this, for this.
Oh,
Right? And for each fragment, which basically is every pixel, it computes the interpolated value of what you output here, and it gives it and calls the fragment function. So fragment function is called for every pixel, is pixel-wise, and vertex function is called for every vertex. I guess it makes sense, right? If you think about vertices as being, vertices and fragments as being pixels, it kind of makes sense. And how does it know? Because what we output here goes as input here. Like this input is not exact, does not coincide with all these positions. How does it compute the input here? It does a lag between the O from 1, O from 2, O from 3, and the T, because there's a lot of stuff. We can have 2. Let's use it. So we use the interpolated O and passes on
that as I here, right? So now if we write I dot UV, it makes sense because O has the UV and because we basically defined it there. So we can use this UV. Let's do something funny. Let's just output a flat color. This is the first thing I do just to make sure that I cover the entire screen, right? I'm gonna remove all this mambo jumbo and do a return float for 0.5000. Now that would be a red, half red. And nothing happens. Well, that's because we haven't done any code that draws that screen and renders the material. So we have to do that. Let's create a script. And where do I create the script? It's scripts. Great. Look, I have one already, but we're going to ignore that because we're going to create it from scratch. Color grading, and we open this, remove all this stuff we don't need, and if you remember from the presentation, we need to hook here on render image. In other words, here or here. I'd like to hook here, not here, because I don't want my skybox to be rendered after my effect and transparencies and everything. I want to take the actual final image, right, and do something with it. And the difference between placing yourself here or here is one attribute you do. But first, on render image, and we have a texture render texture source, destination, and Unity now will call this function whenever it renders, usually at the end of the entire rendering pipeline. So it's a perfect place for us to do color grading because we catch everything. Yeah, but we'll drop this on the camera because we also need just to.
So basically, you render requires a component.
Yes, this is exactly what I was doing. Thank you for reminding me what I'm. And we do a type of, not typo, type of, and camera. And if we want, for any reason, to hook here much earlier, we can use the attribute called opaque, image effect opaque, right? But I don't want to do that. So what
How it will look like.
yeah, you need to have a bit more complex scene to see, and a lot of, you need to have transparencies, light and sky, cube and blah. We don't care about that now. Let's care about on-render image. And what do we render here? How do we actually spit pixels on the screen? Well, let's reference a material. This is the material that will power our effect, and the material that will actually be used to render every pixel on our quad. It's being drawn to cover the whole screen. Should we check for the material? Yeah, let's check the material. And I show you this not because I want to be super safe about this function, but if you have, for any reason, a problem in the on-render image, you must not do just return. Because if you do this, you will get a nice error from Unity saying that on image didn't draw anything. If you also assign it, yeah, we need to assign graphic settings. Doesn't matter for this. Color grading. Put the color grading, and if you press play. On render, it possibly didn't write anything to destination texture, and it's blank, obviously, because we're not doing anything there, and we kind of tampered with Unity here. So always blit something. You can do graphics. You know what the blit operation is? It's a simple copy. It's a name that dates way back in 90 summer, when you would render into a back buffer. So to avoid flickering, yeah, you would render into a back buffer your entire scene, and then flip that buffer onto the video memory directly in one pass, and that was called a blit. It's a simple memory copy operation. It's like mem copy, but here is not just a mem copy, because we're not effectively writing into the frame buffer of the video card. We're just submitting some data to Unity, and Unity will probably submit the data to the graphics driver, and graphics driver will do the blit. But for historical reasons, it's called blit because this is what it does: it's copy and paste. So what I'm doing here is I'm copying the source, paste into destination, just to let Unity know that, hey, if something failed, at least you will get the input unchanged in the output, right? However, that doesn't work always. I know that even doing so, sometimes it kind of cries about that. It didn't cry now. So yeah, let's go ahead and see how we actually blit using that material. Because this is a simple copy. It doesn't evaluate any frag function. It doesn't evaluate anything. It's just a clean copy and paste. But we don't want clean copy and paste. Well, guess what? You can just plug in the the material here. That's it. So easy. Well, we have to do some things first, obviously. Material dot set pass. We have to set pass, and what set pass is that in our material we define passes. So you could have one pass that does something, and you could have another pass that does something else with a completely fragment shader. For instance,
You can make a complete pattern in a single shader.
I'm sorry?
You can complete the pipeline with single shaders or something like that.
You can you can define multiple passes in a subshader, because maybe your shader is not a one pass functionality. Like maybe if you want to do depth of field, you want to grab the screen first, you want to create some incrementally blurred images that corresponds to, as more depth is, the blurrier it is, and you want to interpolate between those. So you would have to have a pre-pass first, where you grab the screen and create all those, and then you would do the final render using all those results from previous passes. So you could have multiple passes, but for what I'm going here, I just need one pass. It's not a problem. So by default, the first pass is 0. All right, and I can even set some parameters to that material. So just for the sake of the example, I will plug in a parameter here. And do we remember how we put parameters? Well, let me tell you. You can basically put them everywhere. Let's test that interpolation. We're going to call T. All right, and I can set the float here. You can see we have set int, set matrix, set float for virtually every type of data we need to pass into the shader. Well, since I have a float, I will pass one float. And here you give the name. I don't like the name I used here. Interpolator. I'll get this like this, and here plug a value. For now, I don't have a value, so I'm just going to put 0. But you know what? Maybe we can put a value here. Let's see. A lot of time when you actually code shaders, you will handle a lot of transport, a lot of data transport. So what I'm doing here, I'm creating this parameter that I want to expose on my effect, on my C# inspector, so that when I change this is transported further into the shader, so that in the shader I can do something with it. So there's a lot of housekeeping work of actually transporting data from the inspector towards the shader. Okay, and how do we do it? We plug it right here. Well, since we're doing interpolation, let's do some colors. Color, left color, or color A equals color dot red. Color B equals, let's see, green, and we have an interpolation going on, and we're gonna duplicate this and say set color, and we know for sure the names will be this, and maybe I'm going to use this name in the shader as well. It's a good it's a good thing to kind of name the shader public variables exactly the same as you would have them in your script, so you can pretty much copy and paste. But as a rule, you would have to have an underscore and capital. It's not something that you're not forced to do this, but this is how I like to do it, and this is how a lot of people like to do it. A lot of built-in variables by Unity respect this naming convention, so maybe it's a good idea to go with it. So since I'm setting these here, I will drop them here, and a color is a float 4. And we're going to say color A, duplicate that, color B, and For now, we've just, we just output a constant red color throughout the entire screen, and let's see if that works. No, it will not work because we don't have a material, right? So we have to create a material. But we did say color grading matte. Yeah, we just have to assign that material.
Your material inside the script, right?
Yeah, so that it becomes the powering material of that particular effect. So what do you think is going to happen? We press play, full screen red, yes. And the nice thing is that once you press play, you can actually go here and change the code in real time, and it will instantly update. It's so much faster than anything. And I have a bad experience with Unity when you can press play, change a C# script, and then it would compile. Sometimes it will crash, but it never actually crashed when I've actually changed shader script. So that's good to know. But we'd like to see this effect without pressing play. Maybe we have some heavy scene. We don't want to see it. How do we make this effect work in view, in scene space? I mean, here in game it will work, but when we design, we'd like the effect to be here as well, and eventually not with playing. Well, I know for sure you can write something like execute in edit mode, and what this does is that basically execute every time. Now you don't have to press play. It works without even pressing play. But we still don't have it in the scene view, and we might need to work with it. Maybe you want the effect to be seen in the scene view. We can add another attribute, and it's quite a specific attribute, and you would have to test if it's Unity 5.6, but I'm not going to test it. I will write it anyway. And it goes something like image effect allowed in scene view. And what this will do is, when we will assign whatever we'll do here, these changes will be propagated to the camera in the scene view, and you see already they have been propagated. All right, so now we have a working post-processing effect that actually works without even playing and works in scene view, and that's great because we can see instantly every change we make. Great, let's do some change.
So let me recap. So
Recap.
you set the pass, the pass from the shader.
Yeah, which corresponds to my first pass.
Okay.
But if you have one pass, it's 0. And you're
And after that you have passed by 3 properties. You
Yeah.
separate the color,
Just-
color B to the shader.
taken from there, put it here.
Yeah.
And then blit using this material, which will force the renderer to not just literally put on the output on this, but it will also evaluate the frag function, the vertex and the frag function of the shader of the material. And if we remember, the material here was created using our own shader, right? Using the color grading shader.
Okay, but the material is named for this is the
But you can name the material whatever.
How do you couple this material with the material that you have
It's a parameter in the script. It's this. I've exposed it as a public property of the script, of the color grading script, right?
oh, okay.
It's public.
I didn't
It's this one. Usually you would do something like material private, and you would create the material internally here. But just to be faster, we've created it by hand.
I didn't catch that assignment, and I didn't
All right.
understand how did you.
Okay, good point out.
Okay.
All right. Okay, let's interpolate that color and see how it works. So instead of returning this color red, I will return either A or either B, but I want to get a mix between those. So I will do lerp, color A, color B, and obviously, right? we're not actually doing a post-processing effect now. We're just interpolating colors just to give you a sense of what that does. And you see, it's 0. You know what? Let's leave it like this for a moment. And as we move towards 1, it goes through yellow, and when it reaches 1, it gets the second color fully. But what if we go to minus? Well, we can't really see it, because we have a high dynamic range camera. It's clipped at green. But if you would have an effect that uses the high dynamic range, the extra dynamic range created by this color, you would see a big fat bloom, because basically now the value that is being output to the screen is no longer in between 0 and 1 for each channel. It far exceeds 1. But we can't see it because we have this well, we don't have a post-processing effect that makes use of the high dynamic range. The point is, in 0 you get red, in 1 you get the second color, and in between you get exactly half mix between those. That's a little interpolation. All right, but let's do something more interesting than just interpolating colors and drop them on the screen. For once, I like to actually visualize the UVs so that I make sure that it makes so that I get a validation of the fact that I'm actually getting all the pixels from 0, 0 to 1, 1 to 1, 0, 1, 1, and 0, 0. And how do we do that? We return a float 4. Always return float 4. Because yeah, I know, but yeah, you would have to also flip the Y based on how Unity starts the Z. Not going to do this now because and how do we get the screen position basically? Well, it's in this variable, right? The UV that is generated by the interpolator when it draws this, when he does a blit, and it's a bidimensional unit, so coordinate. So it has X and Y. Usually you could write this, but just to be safer, you would write this, and you have to plug in 2 more parameters, because this will be like writing i.uv.x, separator i.uv.y, and I don't want to waste time, which I wasted just by saying it, but doesn't matter. I plug in a float 2, which gets the red and the green. Yeah, and now the third parameter is blue, and I want to keep it all at 0. And the last parameter is alpha, which is not important here because we're writing to the final buffer. And we have this. And you have to flip, right?
Yeah.
You have to flip. I mean, the red goes from X to Y. This is black. It means the red and the green are zeroed out, right? And here, I mean, no, it's fine because it's fine for me. Sometimes you need to know if Y starts from top to bottom or the other way around. But for what I'm doing here, it's not important. And what am I doing? Okay. Oh, sometimes I would comment this because you have to be you have to do sane checking. Sometimes things break and you have to debug, and it helps to know, well, maybe there's something wrong with the UVs, maybe something else, I don't know. But how about returning the exact same color? Because if we are able to take the input color and to output it, it means we can also change it in the process, right? So how do we take the input color? First, we need to define the input. Where do we read from? Let's read from a texture, and we'll see sampler 2D. Oh God, I think it's right. And we'll give an input texture. And what do we have to do with this input texture to work? I have to assign it, right? I have to plug in something in the script. And what do we plug into this? The source, exactly, right? You have to. This function assumes that you will read from source and write something into the destination. And whatever you're writing, it's your own responsibility. So what I want to do is, I want to go into the material, set the texture. We know the texture name. It's input text, and we just plug in source. But how do we, I mean, why did this work? I mean, could it not take it from here? No, it couldn't take it from here, because you see, the material, what you do in the material is your own business. If you decide you want to read from a texture called input text, it's your own problem. Basically, this information here is irrelevant at this point. You're reading from source, and the way you plug and the way you bridge Unity with your shader in terms of source is through this variable that you wrote in yourself. Does it make any sense? Yeah? So what do I do here? In onRender image, I take the source, I put it into a texture, I assign it as a variable into my shader so I can do stuff with it in the shader, right? And what stuff will I do with it? Well, let's take float for input color equals, and this is the important piece. You have to sample the texture at a certain position. Do you have every information required for this operation?
Should I have the UV?
You have the UV, so yeah, that gives you the position in the texture, and you have the texture you just assigned, right? So you can read from the texture you have just assigned at that specific input position. And how do you do this? It's text2d, and you have to input a texture, a sampler, and the new v, which is obviously this, our interpolated UV from the triangles. And this is basically reading the background, right? You can do stuff with this. For instance, float output color equals input color, and I return output color. I know I could have returned directly the input color, but just for the sake of flow, I will do this, right? We should have nothing. Well, it's way too much nothing than I expected. It's more nothing than. What's the problem? There has to be a problem. So we assign the input texture to be source. We set the path. Oh, but this shouldn't matter. I usually put. No, it doesn't matter. We have to set the render target of the camera. Of course, you can cache this component so that you don't have to do this. You don't have to do this every frame, but I will do it anyway. So, camera dot render target. So, camera has a target texture that it renders onto. Okay. So we must instruct the camera to render on the destination, if I remember correctly. No. Oh, so there. Oh. No. I think that was correct. Null. I think I know what's happening. Okay. Return output color is input color main text. IUV.
You can go back to the C#.
No, I'm going to go back to my other implementations. So, color correction. Yeah. Render texture is a global texture that you have to assign to destination. With the destination, it's actually instructing. The current camera render texture, make that texture active. Are you sure? Okay, good. Hopefully, if not, it means we have a different kind of problem.
I think the naming is different.
Now let it compile. It compiled and still didn't do anything. When you show something to people, that's when it fails. So, okay, rendering the whatever.
Can you test it on play?
Sorry?
Can you test it on play? Can you play it?
Yeah, I can play it, but
Maybe it's just in the viewport?
So we have input text, right? We have the input text and we have set pass. Set pass 0.
That's the text in the shader set to separate to the text.
No, it has to be a sampler to the.
I don't see.
Okay, let me take a look in the other screen space test. Oh, okay. Maybe. No. So what have we done here wrongfully? Text to the input text YUV. That's working for sure. Return C. So for sure we have correct. So set pass 0 interpolator, no? Set pass texture, set pass blit. Okay, let's put the set pass in this particular order. Render target, although it should not matter. Not material. What am I doing here?
So, underscore input text, do you have it on shader? You have it, right? Have you used it on shader? Underscore input text.
Oh God, this. Okay. Look what's here. It's main text.
Yeah.
Freaking main text.
That's what I was trying to say, but you were too easy.
Okay, yeah. Because Unity by default, creates a main text for you. I don't want your main text, man. Screw you, your main text. Yes.
Yeah, that's all.
Yep. Great. And now we can go back a gazillion years ago, back square one. Let's do something nice with this color. Unity said, let's revert it. 1 minus color. What will this do? We'll reverse the colors. Not very interesting. Let's try something else. Let's try contrast. No, let's try desaturate. And to do that, we'll just pick every component, add them together, divide them by the number of components. Yeah, and by this time we have black and white. It's a little too soft, so let's strengthen that up. We multiply it by a scalar. In fact, let me use the interpolator here. Okay, multiplied by the interpolator, and finally we will add.
So you will multiply back and white by the interpolator, right?
Yeah, for now let's leave this, just multiplied by the interpolator. Let's see what that does. The interpolator is at 0.5, So this acts as a contrast, but the contrast point. No, literally.
That's exposure. Just multiply. You don't take the extremes. You just.
Yeah, I know what you're saying. But contrast is multiplication and brightness is addition. Although these are interchanged, like brightness could be, in most of the case, brightness is gamma, which is bullshit. It's gamma, it's not brightness. Brightness is a constant lift, while contrast is it's a slope change. Because, let me show you. If
You do contrast functions with powers.
No, that's wrong. That's not a contrast. That's gamma. Power is gamma. Yeah. For instance, but it changes the contrast, but it doesn't change the contrast linearly. And contrast is a linear function. Let me show you. Pow, this, and interpolator. Let's make sure this is 1. Yeah. And as we move on, this looks as if we change the contrast, but really we've mapped the colors in a non-linear way because the power, instead of now, if our colors were like this, now they're like this. That's not contrast. Let me show you contrast. It's gamma. Literally, this is gamma, right? Gamma. But they say brightness because it has also brightness and contrast, and you really can't figure out. Yeah. But you can easily check if it's gamma or not. If the black stays at that same level and the white stays at that same level, and only the middle changes, that's gamma. So I will add another. No, I will not add another one. I will return to what we were doing. So that's a contrast, and I will do a lift. And the reason I do this. So let's take this for the lift and multiply with 3 to have a strong contrast. So when lift is 0, we have what I would call a strong contrast. But you said, okay, it's not contrast because it's just a slope change. That's the contrast. Now, if I do lift back, you see, that's the contrast. But I move the contrast center point when I do this lift after the contrast. So now it becomes genuine contrast. If I take this value, you know what, let's add another one. So I usually never do this. I really don't do that. I have to do it now for the sake of, speed. But I hate to do this. Interpolated 2.
Best name.
Yeah. Okay. And use this for the lift, and the other one. No, first for the lift. This is the worst pasting in history of all pasting. And now we have proper brightness and contrast controls. Hopefully, if we compile, see how hard it compiles the C# script. So why the contrast? Why the first is contrast? If you have the lift at exactly 0.5, this is the same image, but it has significantly less contrast, right? If you increase the contrast and you bring down the lift, you get higher contrasting values to the point where you get black and white almost, right? Almost like a threshold function. Black and white. So this is the contrast, if you wish, but we don't care about that yet. Let's do something even more exciting. We have 10 minutes. I think we can do that. Some effect that is not just color grading related. I will attempt to do a blur. How do you blur an image? Oh, but we're in screen space now. I give you a photo. How do you blur it?
big pixels and just make a medium, like an interpolation, but you have to spread it out.
Average out the pixels?
Yeah, average out the pixels. And the more pixels you average out in geometric terms, yeah,
The radius of
the radius of the blur, it will be more. Now, my laptop here, it has an Intel 620, so it will not support too many samples. Will break, but let's try it anyway. So how do we do that? We must start with something. We start with the output color.
So in case we go offline, it means that your laptop got snapped.
Yeah, but I hope and pray to not happen that. So we'll do 2 for loops. We'll do the y for loop, int y equals minus ray y we go to, or we could just say r plus 1, but I don't want to write r plus 1, and y plus plus.
What is
R is a variable, is basically the ray of the blur. So, okay, int radius equals, I will try 3, but I'm not sure if it will work. Let's duplicate this. Usually what I would do, I would actually cache these offsets into a linear array and just do one loop with the positions, but you know, we don't do this now, so let's just do this. You have any idea why it's faster to read like this instead of like this? Do you know why it's faster to read memory like this instead of like this? Why? Because of caching, yeah. Yeah. So it's actually better to put the y, to address the y first and the x second, so that you get the for loop will run like this instead of running like this. When it runs from one line to another, it skips cache, and it's
on the CPU, right?
and it's faster to actually go in a linear fashion in the memory. Just a small. That guy taught me about this a few years ago. Low level, right. Okay, so let's accumulate, right? We need to accumulate the colors. Plus equals, we sample this. We no longer need the input color. We sample this, but we don't just sample from exactly the same XY position. We need to sample it, deviate it, because we need to, basically what we do is, for every pixel that we need to create a blur, we need to sample the region around the pixel and create one single pixel out of that. So we have to deviate a bit. So we'll say float to x and y, and we'll multiply with a very, very small number. Ideally, you would multiply here by the texel size, but I don't have time to compute that, and I will just multiply by 0.001, so that we don't skip too much. Remember, 1 means the whole screen, right? So you would have to, usually you would compute the texel size based on 1 divided by screen dimensions, and you would multiply by texel size, but let's not do that now. And we have to divide the final color, because we accumulate a lot of light. Yeah, we have to be energy conservative here. So, to do that, we have to divide by the number of samples. And how many samples did we have? Well, let's compute how many samples we have horizontally and vertically. It's the same number. And sample is radius plus radius plus 1. Right? Okay, and the number of samples, total number of samples, is this multiplied with itself, right? Because we're doing bidimensional accumulation. And now we divide the final color by this, and we return the output color. Let's pray it works. Well, way to go. It does work, and well, it didn't crash, it didn't freeze, so we can go crazy about this. Oh, it's still working. Not yeah, but
You can add that to the right side.
to
I mean the 8. The 8 version, you can add it to as color A, color B, property of the...
oh yeah, sure. Or maybe we can do the we take the interpolator A and multiply this. Crazy multiplication. Let's go 32 samples and 0.0 multiplied by the interpolator, and we clamp. Yeah, you know what? Don't clamp. Just cast the int, and that's it. And look how smooth this baby is. Yeah, we go too much. Oh, I forgot the interpolator can go to case in which, yeah, it will freeze, because now for every pixel we sample how much? We have 32, and this is almost 1.5. We have 48 by 48, so 50 by 50, 200 and 500 samples for each pixel. This is the worst possible implementation of a blur, but it's it is what it is. So I wanted to give you a glimpse into raymarching, but we definitely don't have time now. Maybe we'll have a follow-up on that.
Short question. Can you apply that material onto the object only to have the object blurred? No. Like the shader on the
Interesting that you've
of the object.
yeah, but then who's assigning the input text? Yeah, that's not funny. Although, let me show you something real quick. We'll do 0 here, and this will be some sort of a next time we will see this. Hopefully, if I can connect into my PC at home.
And now I should say next on GDDI.
Yes, next on GDDI, we'll be showing you something you've never seen before. Look at this. What do you think this is?
A room or
True?
it's a room?
It's a shader. Just one shader.
Ah, okay. So you applied the shader on.
But the shader is camera aware, is world aware, and you know what the interesting thing is? It responds to light. So this is geometry that, if I take my point light, now if I create a new point light here, let's create light, point light, and I'm just gonna go with that light and align with the view. Yeah, and now I have the light right here. Watch what happens. Yeah. Red.
Ooh.
The fake geometry we've just drawn in Photoshop responds to the light. And not only it responds to the light, it responds to every effect that follows afterwards, like the post-processing stack of Unity. And this is, from Unity's perspective, this is real actual geometry, because if we look in the albedo, we have it. If we look in the specular, we have it. If we look in the smoothness, we have the smoothness written. And we even have normals. But that object does not exist in the scene. It's cube 2, I think. No. It's cube 3. This is the scene. Just see, just this. Yep.
Okay, so the shader makes the...
Yeah, the shader makes the entire thing possible. And if we enable this back, bam. And it's just one shader, raymarch shader, that shoots ray into the scene, understands the scene depth, so it kind of it knows where to write, when to write, and when not to write. Let me show you another one. Hopefully I'll do. Okay, check this out. So if we disable this, overlay command. Yeah, screw it. I don't have that, but I can show you a movie. I'm in the middle of developing and raymarching ocean. Look, basic. This is a raymarching ocean, and you see why it responds to the scene reflection. And in this implementation, I wasn't implementing refraction, so you saw a weapon, but it's not very well rendered. If we look to the water has subsurface scattering, so the light that comes from the sun goes into the water, and the water is being lit. Yeah, and that's an actual volumetric rendering. You can change, of course, the color of the ocean.
So the ocean is a shader, right?
Yep, just a shader.
And
That's it. And you can move the ocean, you can scale it, rotate, you can create a wall of ocean. And yeah, hopefully we'll be showing some stuff that's it.
nice.
Okay, there is a question.
Sure.
I'll let you read it.
Oh boy. See. But there are lots of questions.
No, it was already focused here. You shouldn't have moved.
But that wasn't a question.
No, I'm trying to implement that one.
I'm trying to implement a dynamic grass system, Zelda Braille, but I have no idea where to start. Can I some books, tutorials? I am hard stuck here. Yeah, sure. Contact me on Messenger, I guess.
Okay.
And we can talk. We can talk about it.
Okay.
Obviously, it's a broader subject to discuss now, and we don't want to keep everyone here. But yeah, if anyone is interested in something particular, you have a problem, I don't know, you want to create something and you're stuck somewhere, just hit me on Messenger, on Skype or whatever. You'll get my contacts in the presentation, and you'll get some freebies as well here. There's a website as well. You will see there some things, but you can get to me with this final page in the presentation.
You will post this to the...
Yeah, I will post it. Yeah.
In the event, so everybody gets notification.
Yeah, sure.
When,
Yeah, sure.
when you do
Sure.
it.
Yeah.
Excellent.
All right.
Okay.
Questions? If we can allocate 2 or 3 minutes to
I
questions.
just need to process the information that you provided. So as a recap, the shader is part of the material, so right?
Every material, actually, it goes like this. Any material, have a material, right?
Yeah.
This is your material, but the material is nothing but a data storage.
Right.
You just plug in data from whatever, you plug in a texture, you plug in a scalar, you plug in whatever, and this is
Data.
being kept. In fact, a material is a scriptable object. You can, it's a mask. It's just like a texture. It doesn't have, but it also points
to the type of shader.
Yeah.
It doesn't contain the shader, but it uses the shader to pass this material block
Are we still
properties.
online?
I don't know, maybe. It uses this
we are on.
to plug into the shader, and shader takes that information and does it.
So navigates not a composition.
Yeah, it's like a subsystem. You have, but the shader. Remember, the shader is code that is being executed, is being uploaded and executed on the graphics card. So what we did
You.
on GPU, exactly.
Oh, that's the reason
Yeah, that's the-
faster than the
Yep, yep.
script which is running on
If I would have done that blur on the CPU, dead end, dead end, boys. You can't do that.
Okay, so shit. Oh.
Yeah, that loads on the and the bridge between your C# scripts, and the bridge between the CPU and the GPU is within this material property block, where you actually plug in those properties. That's the bridging between. Yeah. Any other questions before we close the deal? Or you can let it process, and maybe next time when we'll do the follow-up, we'll address other questions. Right.
All right, thank you.
Okay.
Yeah.
Thanks for coming, guys.